Let's solve this question together. Which force on the wall applied at point P, this is the point P, will make the net torque 0? So here, in order to solve this question, we need to know about the torque. What is its definition? So torque is defined as the cross product of two vectors, the radius vector and the F vector. And what is the radius vector? Radius vector is a vector that points from the pivot to the applied point of the force. And by the definition of cross product, we can find the magnitude of the torque itself is equals to the length, the magnitude of the radius vector, the magnitude of the force vector, and the sine of the angle between these two vectors, and we can call this sine as the theta. So let's make it very clear here when we look at an example. Here we have that they have three forces for us already, acting at three different applied points here, and then we need to find another fourth force. Then if we add them together, we have the net torque 0. So now let's try to calculate the torque for each of the force itself, and then from there, if we add them together, we can know which should be the other force that can make the net torque to be 0. So let's start from this one first. In order to find the torque here, we need to find the two vectors here. So we have the force vector already, right? And we can see this is the point which is called the applied point. This is where the force is acting on the wheel. This is the contact point, right? This is also called the applied point. That's where you have the force acting on the wheel here. So we need to draw a vector from the pivot. This is the pivot here. That's what they say here from the problem statement, pivot. We need to connect from the pivot to this one. So this one should be the radius. Okay, this is the radius. Let me have the ruler out. So just go from the pivot point to the applied point. Let me make it more accurate here. So this is the radius. See that? This is the radius vector, and the force vector is the red one here. Next, in order to find its magnitude, we need to find the angle is made between the R vector and the F vector. Rotating from the R vector to the F vector, so that the angle can be the smallest one. But we can see what's really special is that R vectors and F vectors are on the same direction, right? So what is the angle that is made between them? 0, right? Yes. So in this case, we got the angle made between this one and the vector F here. The angle itself here is theta. It just turned out to be 0. Then we got sine of 0 is what? Just 0, right? Yes. So in this case, we just got the torque. The torque by definition of this case is 0. Because sine is 0, so everything multiplied with 0 just turned out to be 0. So what does it mean? It means that this kind of force doesn't have any rotational effect. And it's correct, right? Because imagine this, if you're pulling the wheel at this point, you can just then move it, to the left, and it doesn't help to rotate the wheel. So torque is 0 for this case. Then we do the same thing for this second one here. This is the force here, and the pivot point is here. What happened is that you can see that the applied point is also the pivot point. So even in this case, we don't even have the vector r. The vector r itself is just a 0. So it turns out that the torque is also like 0. And what does it mean? Any force that applied to the pivot point doesn't help to rotate the wheel. And it makes sense, right? Just like if you try to pick up the wheel at this point, at this pivot point, it doesn't help to rotate it. So the torque itself also like 0. Now move on to the third one. We have the force is in this direction. This is the force in this direction. And again, this is the apply point here. This is the pivot point. So now we need to, oops, my bad. We need to draw the radius vector pointing from the pivot point to the apply point. This is the radius vector. Okay, so now you see what is the angle? Yes, the angle is made between the radius point to the F point. You see that? This is the vector of the radius R. This is the direction. Oops, let me draw again. This is the vector of the radius R. This is the vector of the radius F. If we try to rotate from R to F, we can either go this direction, right? Or we can go either this direction. We go with the way that the angle can be smaller. So if we go this way, this is R again, this is the F again. So if we go this way, this is like 90 degrees, right? If we go this way, it's like 270 degrees. So we go the clockwise. So we got the angle to be 90. Okay. Rotating in such a way that the angle can be the smallest. You can also see that this vectors here and the vector is actually like perpendicular to each other, right? Yes. So again, we got the angle already. Sine of 90 equals to 1. So in this case, you got the torque equals to the magnitude of vector vector R times with the magnitude of vector F times with sine theta. This is 1. So it's actually equals to R times F. So we got the torque. It's different from 0 in this case, right? And we can also see that it's helped to rotate the wheel clockwise based on the angle from here. And imagine, just imagine, if you have a force pulling to the right this way and it touched the rear of the wheel. So it should make the wheel rotate this way, right? Make sense? Yes. So now you see we got some torque that makes the wheel rotate this way clockwise with this magnitude. So what we need to balance out with this for the fourth one is that we should have a torque that can make the wheel rotate the other way, and the magnitude should be the same, to be R times F. The F here is kind of like, is like 2 units, right? If we just assume that the length of this much is like 1 unit of the force, 1 Newton for example, then this one should be like 2 Newton, right? And then the radius here, I will just say that will be like 4 units, 1, 2, 3, 4. Just borrow the schedule we have right here on the page. So let's have a look at these. Now the point of apply is somewhere in the middle here. You see that? So now what we can do is that we can draw the radius vector first. So let's have the ruler. And let's draw from the pivot point to the apply point. This is the R vector. You see, interesting. This is the R vector. So what you see here is that R vectors here is just half of the R vector for the third force. So that's something to keep in mind, huh? Next, we need to have some force that can have the counterclockwise rotation effect, and it have to apply here. So have a look at these. I could go with what? So let's see, let's try. Okay, if we have the rotating in this direction, then you can see that in this direction it will help. You can see that if in this direction you got vector R in this way, right? This is vector F in this way. So you can see the angle here, the smaller one, it should have also a lockwise effect. So that's not A. We don't go with A because it have a lockwise rotational effect. Again, with the B is also in this direction. If we have the F in this direction, you can see this is the vector R in this direction. Rotating from this to be the smaller angle is also a lockwise effect. So we don't go with B either. Okay, now let's try with C. If you have the C in this direction, oh, so now what you can see that if C in this direction, then you got the R in this direction, the force in this direction. So the angle for now is at 180. And sine of 180 is also like 0. So that's why this one doesn't have any rotation effect. The torque for this one should be 0 as well. So we don't go with C. We only have D and E F. So D and E in the same direction, right? So let's have this one, the F vector in this direction, upward. Now we can see that vector R in this direction, rotating from this to have the smaller angle. That should be 90. So now you see this one is counterclockwise, right? This is the R vector, this is the F vector, this is the 90 degree. Yes, so now we see this should be the good direction. And we have the angle also like 90, right? And sine of 90 is also 1. So then the torque in this way also like R times F times with sine theta, which is 1 here. So we can see that this one will be like it's kind of like the same equation with this one, but in order to distinguish them, how about let me add some labeling here. This should be R1, this is the F1, this is the torque 1, okay? So this is R1, this is F1. This is also the R1, this is F1. We know that we want the torque number 2, which is also equals to R2 times F2, because this is what we find from here. This is torque 2, R2, F2, this is the R2. It should be equal to this one. But we can see that R2 is half of R1. So in order for them to balance each other out for the product, we should have F2 as twice as much of F1, right? So that's what I would go with the D, right? Because D is longer. So let's draw D in here, then we can see it better. D from this one, it should be twice as much of the F1. So this is F2. Okay, so now you see, makes sense, right? This one is twice of this one, and this one is twice of this one. So when they multiply each other, they should balance each other out. So what we see is that one helps us to rotate lockwise, the other helps us to rotate counterclockwise. So that if we add them together, we can have the torque equal to 0. Or we can also apply some algebra values here. If we say rotating by the counterclockwise to be the positive, so then the algebra values of the torque number 2 should be greater than 0. The torque of the K number 1 should be less than 0. So when we add them together, they can make the net torque to be 0. So the final answer is D. Okay, so this is the answer. So I hope that everything clear. Please let me know if you have any question. Thank you.